Oh, yeah, they're ridiculous. Yeah, I mean, just the root canal is $1,000, and then you have to have something done with the tooth, either a crown or a bridge, or unless you just want an empty gap in your mouth. I mean, that's always a possibility too. This Rockwood finally arrived. Let's see. Okay, we'll get started here. You have the test back. The solutions for the test and for the will be posted by Wednesday. You need to look at any of the solutions. And I think the biggest issue that I found with the test were that some difficulties with getting the correct limits of integration on some of the problems. I think that was the number one follow-up. If you had a follow-up, that was it. And then the solutions for the take-home quiz are also they're posted. So anyway, that leaves us in the home stretch here. We're at the last unit, and there's only 3 weeks, basically 3 weeks of class left. And the last week we'll have it's probably Wednesday or probably Friday of that week we'll have the last test. We actually have a class on a Monday, May the 5th, I believe. And that has to do with having Mondays off and all that kind of thing. So I plan on, my plan right now is then I'll be grading those tests and handing them back to you so you can have them to prepare for the final, which will be a full week later on May the 12th. And we'll talk more about that later. But, well, I guess I will just say that the final essentially will be similar to how I had done the final last semester. I'll take some questions from each of the tests. We'll change just some numbers, okay, and that'll be the final exam. Okay, so obviously the best way to study then is to study the problems on your test. Okay, this unit then it has to do with vectors. So for those of you into physics or wanting to go into physics or engineering, it should be of some interest to you. And it talks about integrating over curves. So it has to do with force fields and has to do with work, this concept of work in physics. It is a definite concept. So what we're going to start with here, this is chapter 16, and we'll start with the first section, which is just introduction to vector fields. All right, and so it let's start out with just a definition of what a vector field is. We'll look, first of all, at the 2D case, two-dimensional, and then we'll look at three-dimensional. So let's look at the 2D. We can have a vector field on what's called R2. Now, R2, I'm not sure if I've ever really made this clear to you guys. R2 means the set of all ordered pairs where each of the components is a real number, okay? You can also think of R2 as the XY plane. That's another way to think of it. So a vector field on R2, it's a function, and we usually denote these with a capital letter, capital F we'll call it, that assigns to each point x comma y in R2 a two-dimensional vector called capital F of xy. So what we are talking, and we'll look at some examples in just a couple minutes. So what we're talking about this is that this function of x and y is equal to a 2D vector. So it's got two components, the I and the J component, and each of these components then would be scalar functions of x and y. So for the I component, well, we could have some function of x and y that is multiplying the I component. And for the J component, we can have another function, we could call it Q, that's multiplying the J component, all right? Okay. Or if we want to do some shorthand, we can call F is equal to PI plus QJ, for some shorthand. And then 3D, it's the same kind of thing, except we're just adding an additional component. So a vector field, wait a minute, what's going on here? Oh, Jerry, they can turn in the homework either this Wednesday, or if they don't have it done, they can also turn the homework in a week from today. Either way. Okay, a vector field on R3, 3 dimensions, on R3, and that's just the 3 components, x, y, and z, again, is a function, call it capital F, that assigns to each point, and this time it's x, y, and z, a 3-dimensional vector that we're calling capital F of x, y, z. So this time, our vector function is going to have an I component, a J component, and the K component, and in front of these will have some kind of function of x, y, and z. So we can call this first one, say, P of x, y, z plus Q of x, y, z plus, say, R of x, y, and z. All right. And again, shorthand, we can write capital F is equal to P times the I component plus Q times the J plus R times the K component. All right. I've got something here that helps kind of visualize what these things can look like. And, okay. All right. So what we have here, this first one is in 2 dimensions. So we have a vector field in 2 dimensions. So what we see here, remember that vectors let's reinforce this. The vectors have magnitude and direction, right? Those are the two things, magnitude and direction. Oh, you're right. But I'm saying magnitude and direction. All right. So anyway, so therefore, if arrows are longer, that means bigger magnitude, and of course, the direction of the arrows implies the direction. So this field here, let's see, the function here, and this is an example of a vector function. It's cosine y times the I component plus sine x times the j component. So those are, in this case, the particular functions that are multiplying. And so, as one would expect with cosine and sine, it appears we've got a bunch of circular kinds of vector fields involved here, where things are going around in a circle. All right? Okay, let's look at a second field here. Again, this is 2 dimensions. And this one is the I function is 1 over x minus 2. The j function is 2 over y minus 2. So, obviously, there's going to be, things are going to be changing when x is getting close to 2 and when y is getting close to 2. Because when that happens, your denominator is going to get very, very small, so your magnitude is going to get very large for that particular component. And so you see here, when we're getting close to 2, either for the y or for the x part of it, the vectors get longer. Okay. So here's another example of a vector field. In physics, a lot of times these vector fields represent some kind of force field, or electromagnetic force, whatever, different force fields. Here we have then in 3-dimension, I'll just show a couple of these. Of course, 3-dimension, impossible for me to draw. But so here we show it kind of rotating around the x, y, and z axis, and we have all these vectors swirling around, so to speak. And this particular vector field is represented as this function. The y component is multiplying I, the z component is multiplying j, the x component multiplying the k vector. Okay. And we remember the k vector is the one that goes in the z direction, the j goes in the y direction, the I goes in the x direction. Let's see, let's just look at another one of these. Okay, here's another field. And let's see what this one's like. Okay, so here, this one, we've got, that's interesting. So we have the first function is x times sine y, and then x times cosine z, and y times sine x. Let's see, I see that if we look down here from I guess that would be looking down from the z direction, things seem to be going in a circular kind of direction from that way. Looking at it from almost like horizontally on, it looks like each of these swirls of circles are like in different layers of some kind. So I guess the vectors get very small in other parts of it. I'm not sure, but it's an interesting pattern. So that gives you an idea here. I mean, these vector fields can look very different, obviously, depending on what kind of functions we have. Okay. Now what's going on? All right. Oh, okay. I don't know if I guess I can see that. Okay. All right. There's a particular kind of vector field that is going to be coming up, in the next few sections, and that's from the gradient of the function. So they're called gradient fields. All right. So remember, if we have let's first of all look in 2 dimensions. If we have a function of f of xy, then the gradient, and remember that's an upside down delta, the gradient of f, or grad, G-R-A-D, is equal to, remember this vector, fx times the I component plus fy times the j component. Or another way we can write it is with those brackets there, the vector fx comma fy. So hopefully you guys, it hasn't been that long ago, remember the gradient. So for this function then, we have an associated vector field that we can make based on its gradient. And then also, of course, in 3 dimensions, if we have a function of x, y, and z, then the gradient has got 3 components, fx times the I, plus fy times the j, plus fz times the k component. Or again, I can write it as with the brackets fx, comma, fy, comma, fz. All right. So this gradient f is a vector field. I want you to take that away here today, that we have that. And let's just look at a particular example of showing that. And this shouldn't be anything new. Let's look in 3 dimensions. Say we have a function f of x, y, z that's equal to, say, 2x times the natural log of 7y minus 4z. All right. So associated with that is a 3-dimensional vector, the gradient. And so let's see what we get here. We know the first component is going to be fx, the second is fy, and the third component is fz. So for fx, everything y and z are both considered constants. So fx, the x will go to a 1, and the rest of it stays. So we're going to have 2 times the natural log of 7y minus 4z as our first component. And then for fy, x will be a constant, z will be a constant. So we're going to keep our 2x and then do the derivative of the natural log, which is going to be, what, 1 over the function 7y minus 4z. But then what we also have to do, we have to use the chain rule and multiply by the derivative with respect to y of this function. And so we're going to have a 7 up here. So of course, this top part would simplify to 14x over 7y minus 4z. You finished? Thank you. And then finally, fz, which I haven't left myself enough space for here. We're going to keep x constant and y constant. So again, we're going to have 2x is going to be sticking around, and then we're going to again be doing the derivative of the natural log. So we'll be putting 7y minus 4z in the denominator. And of course, we'll be doing the chain rule, this time with z. So we'll be multiplying by -4 up above to give us a simplification of -8x in the numerator. Okay. The last thing in this section then, this section is pretty brief, is this definition of what is called a conservative vector field. And this is a definition that we'll be using in the next section. So just kind of keep this handy. We'll be referring to this definition again. Definition, a vector field, capital F, and I'll also put Sometimes I'll forget to do it, but some other times I'll remember to put a little arrow on top for a vector, all right, is called a quote-unquote conservative vector field if there is some function, we'll call it small f, if there is some function little f such that the gradient of that little f function is equal to is the same as our vector field. So in this case, we're saying that we're given a vector field, and if we can find this function small f such that its gradient is equal to or the same as our vector field, then we have what is called a conservative vector field. So we'll be referring to this again. Okay. All right, and that's all there is on that section. I plan on ending about 10, let me put a note here. We're doing our class evaluations today, so we'll be ending around 20 to the hour. And I also want to just put a reminder here that, again, there's homework. Homework due this week, and you guys, since you're off on Friday, you can turn it in either on Wednesday or you can turn it in on Monday. Okay? All right. All right. So this next section then, 16.2, introduces what is called a line integral, where we're integrating over a curve. Okay. So now section 16.2, and this section's fairly lengthy. We certainly won't be finishing this section today, believe me. All right. Okay, what we're going to do in this section is we're going to integrate a function over a curve. A function over a curve, and we'll usually be calling the curve capital C, right? Now, the curve is going to be given by parametric equation, okay? We have an x, we have a y if we're talking about 2 dimensions. If we're talking about 3 dimensions, we have x, y, and z, and each one of those components can be represented as a function of a parameter that's usually called t, all right? So here we have this. So the curve C is given by parametric equations. We've had this concept before. X equals x of t, y equals y of t. For right now, we're just looking at 2 dimensions. All right. Where t is our parameter, and t ranges, say, from some number a to some number b, where t is bigger than or equal to a and less than or equal to b. Okay. Now, there's another way we can represent this, and this comes up quite a bit in this section. Another way to represent this curve is by a vector equation. So let's recall what we're talking about with that. Okay, we're going to say here that the vector equation usually represented by small r, got the little arrow on top, small r of t, t is our parameter, and this is equal to some function of x, some function x of t times the I component plus some function y of t times the j component. All right. All right. Or another way of writing this is with the bracket x of t, comma, y of t. And again, t goes between some numbers a and b. Okay. So the difference here between these two is just kind of almost a semantic one. With the first way, we're looking at it as a point, all right? The point xy, where we say x is a function of t and y is a function of t. That's the first way of looking at it. The second way is this. We're looking at this point as a vector coming out of the origin, all right? And so this is the second way, where this is our r of t vector, and its tail is at the origin, 0, 0. So it's going to be equal to, this time now, the vector with these two components, x of t and y of t. So that's the difference. One's treating it as a point, the other one is treating it as a vector. Right. Which do you think? Yes, the first one. The one that has those brackets, you either have brackets or you have I and J, that's treating it like a vector. Okay? But it represents the same point. It's another way of representing this point in space. Either as an arrow from the origin pointing to it, or just as a point. Okay, same thing. All right. Okay, let's look at an example here. Let C, our curve, equal the upper half of the unit circle. All right. So again, we're still in 2 dimensions. So we're talking about going from here around to here, where this has a radius of 1. Okay? It starts here and ends over there. All right. A parameterization is this. We can say that x is equal to the cosine of t, and y would be the sine of t. And what would be my ranges just for the upper half circle for my parameter t? It started 0, but where would it end? Would end at pi, right, because we're just talking about the half circle. Okay, that's representing it as a point, or we could use the vector equation. R of t is equal to cosine t times I plus sine of t times j. Or again, for that, I can use the brackets, cosine t, comma, sine t. Okay? All right. So just a quick example of the differences. Now, I think what we can at least get going with here is just this basic definition here. Okay. Now, we'll integrate, and we're still just talking about 2 dimensions, okay? F of xy over a smooth curve. Now, a smooth curve means its first derivatives are continuous functions. All right, that's what a smooth curve means. Over a smooth curve, x equal x of t, y equals y of t, where t goes from the numbers a to b. Right. We do what we've done with the setting up of the definition of integration throughout, where we basically divide the curve up into segments. Each segment will be called delta S sub I, right? And I've got a drawing here. Then we let the segments get infinitely small. Then we let the segments get, quote unquote, infinitely small. All right. So here, let's just look at this thing here. All right. So here we have a curve, C, and it's starting at T naught, and it's moving around, and it ends at T sub n. And basically, we are dividing this thing up into segments. So I've kind of darkened the segment right there to represent one of them. And this segment is what we're calling delta S. Remember, the variable S, as in Sam, was used to show the arc length, the length of a curved line in previous semester, okay, or was it this semester? Anyway, S is, we use that variable. So this delta S just means the length of that curved little portion of the curve. Now, delta S, using the Pythagorean theorem here, is equal to basically the square root of delta X squared plus delta Y squared, all right? Because here's our delta S right here. And so we can then do like a right triangle kind of thing. Here's our delta X. Here's our delta Y. Notice this is approximately the case because that delta S is not a straight line. It's a curved line. But when you get really, really small, it gets very close to being a straight line. So I've got that little wiggly equal sign there. So delta S is equal to the square root of those sums. And what's that now? It's delta X sub I squared plus delta Y sub I squared. Sorry. All under a square root. That's the Pythagorean theorem. Now, if I multiply the outside of the radical by delta t, I then need to divide inside the radical by delta t squared. So I'm now going from the square root of delta x squared plus delta y squared to the square root of delta x over delta I squared plus delta y over delta t squared. So I then, on the outside of the radical, I have to have the same thing. If I'm dividing on the inside by delta t squared, I have to multiply on the outside by delta t. They will cancel each other out, all right? Okay. So the bottom line with this is this statement right here, that delta S is approximately equal to this right here. Okay? We are choosing to multiply on the other side by the radical by delta t, and then dividing inside the radical. Oh, you're saying, why don't I then just divide both sides by delta t? Is that what you're saying? Okay, yeah, you can do that, absolutely. You can go from here. That won't help us with the Riemann sum thing, but you're correct here. You can go from here to then saying delta S sub I over delta t is approximately equal to that radical summation. Okay, you can do that. All right. Let's then go back here to, we're going to do these Riemann sums. Okay, we're dividing up the curve. So we then are going to define our integral here. So we have an integral sign, and what you do then, if you're integrating over a curve, you put the designation for the curve down there at the bottom part of the integral sign, right there. So this indicates right here, and notice we have ds for the indicating part, the little length of the curve, ds. This is how you notate doing an integral over a curve. How you notate an integral over a curve, capital C. Now, what this equals here is the limit as our divisions of the curve go to infinity of the sums of where we go from I equals 1 to n. So we're dividing up our curve into n segments. And what we add up on this is we add all these segments together where we are evaluating a function f of xy on each one of these line segments. So here's our function f of xy. So we're getting its value on each of those little line segments, and then we're multiplying it by the length of each line segment. Okay. All right. Now, let's see here. So this is going to be equal to, remember what delta f was equal to up here, approximately. So what we're going to do here then is say this is going to be equal to the limit as n goes to infinity of the summation I equals 1 to n, f of x sub I, y sub I on each segment, and then we're replacing delta s now with this, the radical delta x over delta t squared plus delta y over delta t squared, and then we're multiplying it by delta t. All I'm doing here is replacing delta f up there with what we've shown delta f is equal to in that diagram, that square root times delta t. All right, so we have that. And then basically what we end up with then is this. The integral over c of f of xy ds is equal to this. All right, now here we're going to replace this, since we're doing the limit of this summation, we replace that with an integral sign, and we're going from t equals a to t equals b, the lower and upper limit of our parameters. I'm keeping my f of xy, but actually now I need to represent x as x of t and y as y of t. So let me rewrite that. That looks terrible. F of x of t, y of y of t. And then this delta stuff here under the radical gets replaced by the following: dx dt squared plus dy dt squared, and my delta t gets replaced by dt. Right. Let me write this a little bit better here, and then we'll stop. This line integral is equal to this. Okay, before I even continue with this, let me say this. To evaluate any of these line integrals, we have to have a parameterization of the curve. All right? That's how we evaluate a line integral. So that curve that we're integrating over, we have to get a parameterization of it. And sometimes that is difficult. So we parameterize the curve. We parameterize C. So it's going to be our lower limit of our parameter to our upper limit of our parameter. And then our function that we're integrating, we have to put it in terms of the parameter. So I have to put my x as x of t, my y as y of t. And then we have to have this multiplying or integrating factor inside of our integral now, where it's dx dt, this is from our parameterization, squared plus dy dt squared, all under the radical, and then the variable, and then it's dt. T is the variable that we're integrating over. The parameterization of C is represented as x of t, and y equals y of t. All right. So what we're going to look at, of course, are examples of this, so that this doesn't become just an abstract thing. We can see how we can work with this with specific functions and curves, and we'll start that up the next time, okay? So I'm going to, so class is over, and then I'll hand you out the questionnaire, and then I have to read you something, and then Jenna will take it from there. Where's the question? Here's the thing I have to read. Something I have to read. If you don't, you need to use a number 2 pencil on this. I've got some up here if you don't have any.
Probably in the envelope.
No, I took it out of the envelope. And of course, now I duly packed it away somewhere. Okay, anyway, I'm going to paraphrase what I'm supposed to read. Basically, I don't see the results of this until after final grades are submitted, and then I don't even know who wrote what. So you can be honest without any recrimination. If you need a pencil, there's some horrible pencils right here for number 2 pencils. All right? And this is used to help evaluate classroom instruction.
No, not quite. Yeah, I've already got, we've got evaluations from the high school also, so I've stuffed them on them already in here, so just, you might have to, is that here? Oh, yeah, here. Just, that's okay. Just put them all in here and show, that you do stuff in here, also. Yeah. Exactly. Figure it out. I left her a note. Also, about understanding the note.